Okay. I just screwed that up yesterday, so I want to make sure I don't screw it up today. Oh. Chapter 4 homework is due tonight. Today is the 18th. The chapter 5 homework will be due on April 8th. We have the quiz on chapter 4 today. So the chapter 4 quiz is today. We'll have it later in class. The chapter 3 and 4 exam will be on Monday next week. We will not have a lab that day, but you can do makeups if you need to make up any labs. On all quizzes and labs, you get one sheet of notes, and you need a calculator. I have calculators you can borrow. So, just some quick review. Specific heat. If equal amounts of heat are added to two masses of metal, like iron and aluminum, would they raise the same number of degrees? No, because different temperatures have different properties. Specific heat is the net amount of heat. The specific heat capacity is the amount of heat required to raise the temperature of 1 kilogram of a substance 1 degree Celsius. The heat required to warm something or cool it is the mass times the specific heat capacity times the change in temperature. And this is what applies when a substance does not undergo a phase change. With a phase change, the heat required for a phase change is mass times latent heat. So when you have a phase change, it requires heat to make that change, like from solid to liquid or from liquid to gas. So that heat is latent heat because it's hidden heat that doesn't change the temperature. And so that'll be mass times latent heat. There's a different latent heat for fusion and vaporization. So heat during a phase change from liquid to gas, the heat energy has to be used to separate the molecules rather than add to their kinetic energy. And this is called latent heat. This could also apply to other sorts of phase changes between liquid and gas, between gas and plasma, and other weirder phases that exist out there. And so the heat associated with the phase change from either solid to liquid or liquid to gas is called latent heat. So there's the latent heat of fusion, which is the amount of heat required to change 1 kilogram of a substance from solid to liquid at the melting point temperature. So for water, that's 80 kilocalories per kilogram. And the latent heat of vaporization is the heat required to change it from liquid to gas at the boiling point temperature. So for water, that's 540 kilocalories per kilogram. So heat transfer occurs in a few different ways. So if you're talking about heat, let's talk about the 3 main ways that heat moves. The simplest of these is conduction. This is just heat transfer by contact, or just heat moving through a substance. So here, this metal rod, it's a fireplace poker. This fireplace poker is conducting heat along its length. Metals happen to be good conductors of heat for much the same reason they're good conductors of electricity. The properties that make them good conductors of electricity also make them good conductors. This is partially why metals feel cold. So if you, at the desk here, if you touch the faucet's going to feel colder than the table. So they're almost certainly exactly the same temperature. They both equalize with the room. But because the faucet is better at pulling heat away from your hands, because it conducts heat better than the wood or whatever the heck these counters are made of, it feels colder. So that's just heat transfer by contact, direct contact. The other one, another way you can have heat transfer is by something that is hot moving. That is convection. Convection is heat transfer by the movement of something that has heat. So you get convection when hot air rises or flows around a room. So if you have if you have a heater on one side of the room, the hot air will rise on one side, the cool air will sink on the other, and you get a circulation. You can have forced convection where you blow it with a fan. So like the heater in your car blows air over the hot engine of your car to heat the inside of your car. You may have heard of a convection oven or an air fryer. That increases the rate, the speed at which things cook, the heat transfer, by blowing the air inside an oven, basically. It's just an oven with a fan in it. That's the secret of an air fryer. It's an oven with a fan. And then the last form of heat transfer is radiation, which is light. Anything with a temperature emits light. It emits electromagnetic radiation. The higher the temperature, the more electromagnetic radiation it emits, and at the shorter the wavelength, the higher the frequency it emits it at. This is why when you get something really hot, it glows red. That's black body radiation. That is heat transfer by radiation. So anything with a temperature will emit electromagnetic radiation, which can then be absorbed by other things. So conduction is the transfer of heat by molecular collisions, and how well a substance conducts depends on its molecular bonding and internal structure. So metals have a lot of stuff that can easily move, jiggling through them. So they conduct things very well. Liquids and gases tend to be poor conductors because the molecules don't interact as much compared to solids. And things with a lot of air in them are good insulators. They're very bad conductors of heat. So when you want to insulate your house, you fill it with something that traps a lot of air and keeps it from moving. By keeping it from moving, you prevent convection, but the air itself is a miserable conductor of heat because there's just so few molecules bouncing around, basically. Metals are generally good thermal conductors because their molecules are close together and they've got lots of freely moving electrons and things. For much the same reason they're good at conducting electricity, because they have electrons that can easily move, that can also help to transfer heat. Convection is the transfer of heat by movement of a substance or mass. It's usually a gas or a liquid, so it's usually a fluid. In theory, you can have conduction by moving solids around. I mean, that basically occurs in the crust, in the mantle of the earth. You know, warm rock in the mantle rises, cold sinks, and that dries like tectonic plates and stuff. But it's the transfer of heat by the movement of substance or mass from one position to another. So in theory, you could also move like rocks or something. But most homes are heated by convection. Most homes are heated by the movement of heated air. If you've got a furnace with a fan in it, or a blower of any sort, or an AC system, it's heating you by convection. I mean convection, sorry, not conduction. Bah. And radiation is the process of transferring energy by means of electromagnetic waves. If you've ever used one of those space heaters that's just got wires that glow, you're being heated directly by radiation. That's just, it's a hot wire, it's emitting infrared light, you're absorbing it, it warms you up. So electromagnetic waves, they can carry heat even through a vacuum. So that's the way that heat can be transferred even in the vacuum of space or anywhere. And in general, dark objects absorb radiation well, light objects do not absorb radiation well. They tend to reflect it. Which is why if you go out on a sunny day wearing a black shirt, it's going to feel hot. Wearing a white shirt is going to feel less hot. Because the black shirt will heat up as it absorbs the light of the radiation from the sun. So if you have a good insulating material, if you want to keep heat from being transferred, you use an abundance of open airspace to inhibit the movement of heat, but you also try and keep that air from moving. You try and stop convection. So things like goose down, lots of feathers that trap that air in place, keep it from moving around. So it can't get replaced by cold air from somewhere else, for example. So you're preventing both conduction and convection. So house insulation is commonly spun fiberglass. Pot holders are fabric with batting. There are multiple layers of fabric with packing material in between them. Double pane windows have the space in between the two panes of the window has had most of the gas in there removed. It's basically empty. They usually put a little bit of some non-reactive gas in there so that, doesn't have to hold up against so much pressure from the outside. But that's the general idea there. And the empty space in between, there's a void between the glass panes. So if you want something that stops all three forms of radiation, this is a vacuum bomb, also sometimes called a door flask, or if you like brand names, a thermos. This is made of 2 layers of glass with an empty space in between with the air pumped out. Similar things are done for, those insulating drink cups. They remove the air. They have a partial vacuum in between the 2 layers of glass. And then the inside layer is silvered, so it reflects radiation back in, or reflects radiation from the outside back out to prevent radiation transferring. The vacuum prevents conduction because there's nothing to conduct, and convection because there's nothing to move around and convect. So the partial vacuum between the double walls minimizes conduction and convection of heat energy. And the silvered inner surface of the inner glass container minimizes heat transfer through radiation. And if you want to handle a really big temperature difference, like if you're holding cryogenic materials, like when I was doing my research, I had to take a liquid helium that I had to keep cold. And I was doing things very, very cold temperature. What you have is you have 2 walls like that, but you could also have extra layers of reflective material in between to reflect even more of the radiation. And the walls are usually made of metal for practical purposes. But a quality vacuum or thermos bottle is designed to either keep cold foods cold or hot foods hot. And at the most extreme, you can use it to keep very, very cold things cold, like liquid helium. Or even colder things. Though if you're on colder liquid helium, you need more layers involved. So matter can appear in several phases. The 3 most common phases that you'll encounter are solids, liquids, and gases. Now, those solids, liquids, and gases, well, liquids and gases are just liquids and gases. Solids can sometimes have different varieties of the solid because they can have different crystal structures. That can get very complicated. But the primary thing that determines what phase of the substance exists in is pressure and temperature. There are also some weird phases out there that have to do with other factors. So certain materials, there are certain phases you can only reach at certain magnetic fields, things like that. But normal solid, liquid, and gas, the primary thing is pressure and temperature. Some examples at normal room pressure and temperature. Copper is a solid. Water is a liquid. And oxygen in the air is a gas. But I could heat the copper up to a certain point and it would become a liquid. I could cool the water down or heat it up to turn it into either a solid or a gas. And I could cool the oxygen down in theory enough to turn it into a liquid. And I could do similar things by messing with the pressure. Though, I mean, it does vary, but it's water I can definitely cause to become a liquid but I mean, we give a gas by pumping them, the pump on water enough to make it boil. But yeah. So here is the phase diagram for water. This shows the various states that water is in at various temperatures and pressure. On this side is pressure. This red line is atmospheric pressure at 100 kilopascals. And each step up, this is a log scale, so each step up is 10 times the pressure. And then horizontally, this is temperature. Sorry, this is a log scale. But yeah, each step up is 10 times the pressure. And then across here, this is temperature. Going from, this is absolute zero up to something like 350 Celsius. So going from 0 Kelvin up to 650 Kelvin. And so at lower pressures and higher temperatures, you get gas. At higher pressures and sort of medium, so at higher temperatures and medium pressures, you get liquid. And then at low temperature and very high pressure, you get solid. And then you'll see all these different things that have different letters marking them. These are different forms of solid ice. Because ice is in that organized crystalline structure, the pattern that it is organized in can be different. And that's what these different varieties are here. But primarily you see just the 1H. And then there's some interesting stuff that happens up here above what's called the critical point. You get into this area over here where the difference between liquid and gas is sort of fuzzy. There isn't a strict difference, and that's what's known as a supercritical fluid. You're not going to likely to see supercritical water, but supercritical CO2 is used sometimes actually for certain fancy dry cleaning, because it's particularly good at pulling things out in a safe way from delicate clothes, because it's a good solvent, but it also can act like a gas, so it can get everywhere. Now, in solids, the molecules for heat, they vibrate. They have a definite shape and volume. That is what defines a solid. If I have a solid, its shape and volume do not change unless I do something drastic to it. It's not like I can put the solid in a jar and its shape is going to change or its volume is going to change. Solids come in two types. There are ordered solids, crystalline solids, naturally occurring crystalline solids on Earth. Naturally occurring inorganic crystalline solids on Earth are called minerals. But yeah, one of the requirements to be a mineral is that it has to be a crystalline solid. So a crystalline solid is something where the molecules are arranged in a particular repeating order. Most solids are crystalline solids. And upon heating, the solids will gain kinetic energy. They will vibrate more. And the more heat, the bigger the vibrations, the solids will expand. An amorphous solid is a glass. That is the technical term. They lack a ordered molecular structure. And that also means that they will gradually become softer as heat is added, and they don't have a definite melting temperature. So the 3D orderly arrangement of atoms in a crystalline solid is called the lattice, and the lattice will expand due to increase in temperature. And glasses are weird and complicated. And the outside appearance of a well-formed mineral will reflect the molecular lattice. So here, this is halite, which is sodium chloride or salt. And you can see it's cubic in shape because the lattice is cubic. Name? A liquid is one where the molecules are not tightly bound to each other, but they're moderately bound to each other. So they don't have they have little or no lattice arrangement. So they have but they are still all sort of attracted to each other. So they can move and assume the shape of their container, but they don't have a definite shape. They do have a definite volume, they don't have a definite shape. They don't expand to fill the container just by the container being bare. But if you heat them, they do expand. So liquids will expand when they're heating because the molecules bounce around more and slide around more. And eventually you reach the boiling point when they can break free of the other molecules in the liquid and turn into a gas. And a gas or vapor is when the heat is sufficient to break the individual molecules apart from each other. You reach the gaseous phase when the molecules or atoms are just freely flying apart, not strongly interacting with each other. A gas will assume the entire size and shape of the container. And for a gas, pressure, volume, and temperature are closely related. Now, if you heat a gas enough, you'll actually reach a point where you will rip the electrons from the molecules, the outermost electrons from molecules, and form a plasma of free electrons and ions. And plasmas are like a gas, except everything is made of electrically charged particles, so that there are complex magnetic interactions as well. And so they're extremely hot gas and electrically charged particles. You can make a cooler plasma, but generally they're the most common occurrences are quite hot. There are ways to make a plasma that's not as hot where you ionize it electrically, things like that. But plasmas exist inside our sun and other very hot stars. There's also a plasma in the fluorescent light bulbs above you. And the ionosphere of the Earth's outer atmosphere is a plasma, and plasmas are considered another state of matter. And there's other more complex states as well. There's ones with large scale quantum ordering. You get things like superfluids and Bose-Einstein condensates. We're not going to really get into those, but they do exist. And that's all I really wanted to cover for today. So it is now time for the quiz. So we have the chapter 4 quiz. You get one sheet of notes. If you need to borrow a calculator, I have calculators up here. I will be handing out the quizzes momentarily. Yeah. So if you need to get a calculator, come quick, go up and borrow a calculator. I mean, it's not. Let's see if one of these is. They're all kind of dull. Should have. Yeah. Oh. Oh. Oh, oops.